Hey, so my name is Jason, and I'm one of your plus leaders for Physics 2212 this semester. And this is something we've never really done before. And for today's double plus session, we had this mock exam. So for this video, I will go over these questions in order. Problem one will be distributed charge. And on a test, you will likely see some sort of 2D charge distribution where you're going to integrate and get some sort of area and find the electric field from that area. In this case, we are going to look at a rectangle, which is just made of a bunch of rods. Okay. Problem two is potential difference. And you're on the test, you're going to have to know this for non-constant and constant electric fields. So we're going to see both of that today. Problem three will be circuits. So has some resistors, capacitor, battery, and a switch. We will take a look at that as well as how to graph them. Charge over time, current over time, stuff like that. Problem four is moving point charges. And this one is pretty much Beatt's-Savart law. So before we get started though, here's some things to keep in mind. And it's that this is a mock exam made by your Dear Plus leaders. There's three of us this semester, and if you guys haven't been to a plus session yet, or don't go as often as maybe you should, we really encourage you guys to come to our plus sessions. We're all super nice, I promise, and you can find our schedules at the bottom of the Canvas homepage. But yeah. So this mock exam does not contain old or new exam problems. These are problems that we made, and they are simply our best guess as to what may show up on this semester's exam, at least for the fall 2025 semester exam 2. Every part of every question has been assigned a certain number of points, and because we're not TAs, we cannot tell you for sure if this is accurate or not, so we're just going to say it's not accurate. But generally on the exam, you will see the number of points each question is worth, as well as its subparts. So we kind of try to structure it in a similar way to what you would see on your actual exam. But this serves more as a guide than anything else. So if a question has less points, say it's worth 5 points, then that should be an indication that it takes less time and a bit less work than a question that might be worth 10 or 15 points. And that's kind of a testing strategy you can use on your exam too. If a question is worth 5 points, you know you shouldn't be spending as much time on it as a 15-point question. Now we are not TAs, we are plus leaders, peer-led undergraduate study leaders. So we do not write the exam, and we actually have not seen the exam, but we have met with Professor Greco, who is the course coordinator for this class, and he's given us a lot of hints as to what might be on the exam. So as we do this video, I will hopefully give you guys some advice as well as how to approach these questions. And hopefully you guys, by the end of the video, have a more solid grasp on the fundamentals as to how you guys will approach questions similar to these and the questions on your exam. So let's get started with problem one, distributed charge. And what do we have here? Well, we have a rectangle of length L and height H, and we know it as it's uniformly distributed with positive charge plus Q. So let me just write that here, plus Q. The rectangle is centered on x-axis, yada, yada, yada. All of this is shown in the picture. Cool. Um, of course, when you're actually doing the exam, read each question carefully. But I wrote this exam, or this question specifically at least, and yeah, I'm gonna gloss over that part a little bit. But yeah, obviously read, take your time to read the problems, so you're actually answering the right thing, and you're not forgetting small details. So consider an infinitesimal rod of height h, and with dx centered at x 0, find the relative position vector r, where the observation location is at d 0, so over there. Okay, well, I don't know why that laser is stuck there. Okay, cool. So that was weird. Now, to find a relative position vector, you're always going to take our observation minus our source, where our observation location is, of course, specified at d 0. So d 0, um, subtracted by our source. Where is our source located? Well, it's coming from this infinitesimally skinny rod, and they tell us that it's located at x 0, 0 over here. So super important. This is just the x coordinate of the center of this rod. So maybe it's -3, maybe it's -1. We're going to integrate over it. So that's why there's a variable here. So minus x 0, 0. This gives us a relative position vector of d minus x and the x component, 0, comma 0. And let's, this will be the final answer for part 1. But just for, making our job easier later on, let's find the magnitude real quick. So what is the magnitude? Well, it's the sum of the components squared. So if you do that math, you get that the magnitude is just d minus x, because this vector only has a component in the x component. So this is our magnitude, but this is our final answer. This is because that's the relative position vector. Okay. Now, determine an expression for the charge on an infinitesimal rod, dq, in terms of dx and relevant known variables. This part is tricky, and I got a lot of questions about this on the during the double plus today. So I will address that right now. A lot of times, so just taking a step back from the question, a lot of times what we're used to seeing is some sort of line charge, right? Let's say this is a um, rod or line with length L. And I want to look at a small piece of this rod. So let's call this small length dx. This is what we're used to seeing. And to approach these questions, you might say that, yeah, I know I can find the charge density, right? The line charge density is just the total charge, let's just call it Q, the total charge divided by the length of the rod, Q over L. Now, this is true for line charges because line charges are one-dimensional. They only have length. This problem is a little bit different. This problem is a bit more complicated, but it's the same idea. This question is two-dimensional. And even a rod has some width, right? dx. So keep that in mind. Instead of lambda, we can abbreviate surface area charge density as not lambda, but sigma. And it's still going to be the same idea. It's going to be the total charge divided by the area, which that charge is uniformly distributed over. So total charge is going to be, in this case, positive Q divided by the area. Well, what is the area of this rectangle? It's length times width, which is going to be L times H. Cool. So Q over area, which is area being L times H. And we know that this is the density, right, of the charge across this rectangle. And that density should be the same as the density for this skinny rod. Well, if we were to just look at the skinny rod, and then let's find its charge density. Well, it has charge dq, and it has a height of h, it has a width of dx. So if its charge is dq, and we know its height and width, then we can find its area, right? So the denominator will be length times width, or in this case, the height being h and the width being dx. So this is good because we have charge in the numerator and area in the denominator. So the units and dimensions all match, which is good. And notice that, yeah, this was, we're dealing with surface charge density now. So from here, we can just focus on this part of the equation and solve for dq. Of course, we can see that just looking at this part, we see that h cancels out, and now it's just algebra. So dq is equal to q over L dx. And that will be our final answer for solving dq. Yeah. So we are ready for part 3 now. Write down an expression for the vector electric field dE of the infinitesimal rod at the observation location d00 in terms of the given variables and known constants. So Um, we are looking for the electric field from one of these infinitesimal rods, right? At the observation location. Well, ask yourself, can we find the electric field, or do we know the electric field of a skinny rod? And we actually do. And that's why we should be familiar with our formula sheet, right? So I actually don't remember the formula myself. So I will also refer to the formula sheet on my end here, and I see that the electric field of a rod that's not infinitely long. Notice here, I did not say for this question that the rod is infinitely long or that we're super close to the um, rod. I did not say those things, so we cannot make those approximations because there are two rod formulas, one where R is much less than L, but this is not specified in this question, so we cannot assume that. So we're going to use the more general formula for electric field of a rod. And this is in the top left corner of our formula sheet in the electric field section, where E rod is equal to K times Q over R times the square root of R squared plus L over 2 squared. Now, what are we seeing here? Well, Q is, of course, the total charge. L is the length of the rod. Be careful there. L is the length of a rod. R is what? What's R? R, you might think, is relative position vector, and it pretty much is, except you can't square a vector, right? That's just not a thing. So this is actually, in our formula sheet, R is the distance from our observation to our source. So it's that this distance here. So that's why we found the magnitude of our relative position vector, because we're going to use it here. So with this formula in mind, well, first of all, remember that this is magnitude, and we're looking for the vector electric field. That's why reading the question is very important. So you don't want to go through to find the magnitude and forget to include the direction, right? We know that this is the general formula for electric field of a rod. So we can find the electric field of just, a rod here. And we're going to call that dE, a skinny rod. So, oops, let's say dE, dE is, I'm going to write this as a vector, so we do K. What's Q? Well, we know that the charge on one rod is dQ, so let's plug in dQ for Q over R, but what is R? Well, R, like we said earlier, is the distance, d minus x, so I'll write that in. D minus x is equal to R, so we get d minus x squared plus L over 2 squared. But for this L, be careful. This is not, just because this is also called L here, the length of the rectangle, just because this L does not mean the length of our rod is L, right? The length of our rod is from here down to here. We know that's actually the height of H. So instead of L, I'm going to write H for this rod because we're just looking at the rod. So plus H over 2 squared. And let me extend this over here. All of this is under the square root, so I'll just raise it to 1/2 power. Hopefully that makes sense. I'm just plugging in dq for q, d minus x for r, and h for l. So I'm just plugging things in here. Then we can simplify a bit later. And of course, we know what dq is. dq is just going to be q over l dx, right? So our final expression for dE, if I plug in dQ, should be that dE is equal to k q dx. I'm going to bring L to the denominator. We get L d minus x times d minus x squared plus maybe h squared over 4. All of this is still under the square root, or the 1/2 power. So this is going to be our final answer for part 3. Except not quite. I almost missed it myself. We're looking for the vector. So let's just conceptually reason out what the direction is going to be. Well, I have a positively charged rod here. And we know that electric field points outwards from a positive charge. So when I get to my observation location, my electric field points to the right in the positive x-hat direction because the rod and the rectangle as a whole is going to be positively charged. So super important. This is our magnitude, which we got from this formula, but we still need to include the unit vector, the direction. Okay, next part, set up the integral for the net vector electric field at the observation location from the whole rectangle. Include the limits of the integral, but do not evaluate. So, well, how do we find E? Well, we're looking for E, and that is, of course, we know if we know dE, all we have to do is integrate, right? That's going to be the integral of dE, but we still need to figure out what the limits of our integral is. And as we said in the beginning, we know that a rectangle is made up of a bunch of an infinite number of infinitesimally skinny rods, right? That sounds a little weird, but if you imagine a bajillion rods stacked next to one another, you can imagine that it eventually looks something like a rectangle, which is what we have here. And that's the purpose of integration here. So our lower bound is at x equals negative L. Our upper bound goes up to x equals 0. So our those are going to be the bounds of our integral. So we have x equals negative L and goes up to x equals 0. So let's just plug in. We get the integral of negative L, 0. What is dE? Well, let's write it this way. KQ uh, over L times d minus x times d minus x squared plus h squared over 4, still under the square root. All of this, and what's our variable of integration? Well, it's our dx, which I saved over here, right? And whatever you get for that, this is going to be a scalar quantity. So don't forget our unit vector still. This is all still going to be in the positive x-hat direction. Cool. We're not going to evaluate this because this is a physics class, not a math class. If you did, when you do set up an integral on your exam, it should be an integral that's pretty reasonable to solve, maybe like a sine or cosine, or it'll be some quick use substitution. Or maybe you'll get lucky and they tell you to just not evaluate. We've seen this in past exam problems, right? So for this problem, do not evaluate. The important part is just understand how to find dE, the direction, and the bounds of your integral. And we can check our answer real quickly with our answer key here, which is also provided in the double plot session. So negative L 0, KQ over L d minus x squared, a squared over 4, all to the 1/2 dx. And yeah, that's going to be our final answer. And here in the answer key, I took a bit more time and wrote out my steps a bit more neater and more carefully. So we can refer back to this as we do these problems. Okay, so that is problem 1 down. Now, we did try to include some additional practice questions if you want to see similar questions. This is not comprehensive. You can find more practice problems in the GPS and the homeworks, not homeworks, but the old exams. But these are just some quick ones that came to mind that are similar to um, this problem and what you might see on the exam. So this is Fall 24, Test 2, Question 2, AI Plato, Question 18.4, GPS number 3, Question 3. Of course, all of the past exam questions and all of the AI Plato and all of the GPS questions are fair game and great study materials. GPS, in fact, all of the questions have video solutions. So I really encourage students to look at those because if you get stuck, you can watch a nice video explanation. Excuse me. But um, let's do problem 2 now. So potential difference. Let's see. Well, we have, let me get my highlighter. We have two uniform parallel disks of radius r. This is important because we also know that they have charges positive and minus Q. What is that? Well, hopefully we immediately recognize that this is a capacitor. But let's keep reading the question. Position A is located at distance d from the x-axis, or sorry, from the positive plate. So let's mark this up real quickly. This is a distance of d from the left plate. And position B is likewise distance d away from the right plate, the negative plate. It's also a distance of d. Furthermore, position C is located at distance h below the x-axis. So this distance is going to be h, and position D is located at distance 2h above the x-axis. So this is what's going on. Let's take a look at the questions. Calculate the potential difference VB minus VA. Does your answer make sense and justify its sign? So this is another common mistake I saw people make in the double plus. So let's take a moment to look at it. What does this notation mean? VB minus VA. Well, it's of course the potential difference at B minus the potential difference at A. But what does it mean conceptually? Well, it means if I were to travel from A to B, what is my potential difference? Am I gaining potential? Am I losing potential? What's going on? So maybe that doesn't make much sense. Just remember that it's always going to be V final minus V initial when we write it out this way. So this implies that we started at point A and my final position was at point B. So the notation I actually like to write is saying, okay, if I know I'm traveling from A to B, let's just say this is the potential difference from VA to point B. I just like this notation because it allows me to never really get it wrong. I know exactly um, where my path is taking me. Okay, so what does it mean? Point A to point B. Well, I'm traveling from here to here. So maybe your first thought is to use, maybe you recognize this is a rod or a disc. Well, it's actually a disc. It's not a rod, but it looks like a rod on 2D plane, but it's a disc. But don't even think about that. Think about, okay, do I know the electric field of a capacitor? So first of all, we need to recognize it's a capacitor. A capacitor is nothing but two uniform parallel disks with equal but opposite charges, right? And another special property of capacitors is that when you're inside the capacitor, E field is constant, or in other words, uniform. And um, this actually allows us to simplify our potential difference integral, because when you're integrating over something constant, I mean, you can imagine like an XY axis, if you were to integrate something constant, then that's just going to be a rectangle, right? So actually what we can do is we can say, okay, the potential difference formula is normally going to be negative integral from initial to final position of E dot dl. But if we know that E is constant, if we know E is constant or uniform, then this simplifies to just give us the negative, don't forget the negative, I saw a lot of people missing the negative sign. It's a negative of the electric field, still dot product with the path we take. So instead of dl, we can just consider the entire path we take, the distance, as a vector though, we'll get to that in a second, multiplied by the electric field. So this is how you find the area of a rectangle, right? So that's where this simplification comes from. You don't actually have to think about this rectangle analogy. You can memorize this if you want. That when electric field is uniform, use this formula for potential difference. So how do we find electric field of a capacitor though? Because that's what we care about here, right? Well, let's reference our formula sheet. E capacitor is equal to Q over A epsilon naught, where A is the area of the capacitor. We can plug that in later, but we know that this is a disk. So the area of each capacitor plate is just going to be, it's the area of a circle, right? It's a disk. So pi r squared. We can plug that in later. Not a big deal. So from here, let's see what we're gonna do. Well, we already got this formula, we derived it actually. So potential difference from A to B is equal to the negative electric field dot product with L. What is E here? Well, actually in the formula sheet they give you this as the magnitude, so we have to figure out the direction. Now E of the capacitor is just going to be Q over A epsilon naught, but I wrote this as a vector and a dot product for a reason. So let's not ignore that because that's going to understanding this is going to be crucial for solving the next few problems. The electric field inside this capacitor is going to be pointing from left to right because this is our positive charge. Remember, exam one, electric field points spiky from a positive charge and points in towards a negative charge. So all the electric fields inside inside the capacitor at least, it's gonna be uniform pointing left to right. So I'm gonna just write this arrow here just to help us remember that. Inside the capacitor, I know I'm kind of drawing this outside the capacitor, but it's just a note for us. Inside the capacitor, electric field points in the positive x-hat direction. So this formula is actually Q over A epsilon naught in the positive x-hat direction. Now, don't forget, this is, we have a negative sign here. So delta V, A to B, we are not going to forget that negative sign. And we're taking the dot product of this with our L vector. What is L? Well, L is the distance from A to B. What is that distance? Well, we know the entire distance between the plates is going to be S. So we want to find just the distance between A and B, but we know this is D, so let's just subtract them out. This is just, some geometry. So L, at least the magnitude of L, is just going to be S minus D minus D. So S minus D gives us S minus 2D. So S minus 2D. But I wrote this as a vector for a reason, right? So why is that a vector? What is the vector? Well, we just found the magnitude. Let's also find the direction. So is my path from B to A or A to B? That's why the notation is important to understand. Well, I'm doing from A to B. So that means I'm traveling left to right, or in other words, in the um, positive x-hat direction. So this is actually also in positive x-hat direction. So what we're going to get here is when if I rearrange, because multiplication, I can rearrange things, right? The order doesn't matter. So Q over A epsilon naught x hat. I'm gonna bring the second x hat to the front as well. This x hat dot product with x hat times s minus 2d. And we see that we get the dot product between two vectors because to take a dot product, it can only happen between two vectors, right? So the dot product of x hat dot x hat is going to be 1. Um, and because of that, this term kind of just goes away, right? It doesn't, I mean, it goes away. It doesn't go to 0. It goes to 1. So we can simplify this. It becomes negative Q over A epsilon naught. Now might be a good time to plug it in A. So A is going to be pi r squared times epsilon naught. And don't forget to multiply by S minus 2D. Okay. So this is, this should be our final answer. Now, does our answer make sense? Let's justify it. Now, first of all, potential difference is a scalar quantity. So it makes sense and it's good that our vectors, we take the dot product and we just end up with a scalar, right? Now, this scalar is negative. So does it make sense for this to be negative? Well, it actually does because when we go from A to B, we are traveling with this electric field. So anytime you're traveling with the electric field, you will be losing potential, which means your potential difference is going to be negative. And I do a bit of a better job writing that down on the answer key. So I'm not gonna waste time rewriting it here. But yeah, that's the reasoning. When you go with electric field, you lose potential. And when you go against the electric field, so if I were to go from B to A, then I would be going against the electric field. So in that case, if you go against the electric field, then potential difference will be positive. So just understand that. Let's do the next question, but just checking, yeah, our answer is correct. Yeah, I guess I plug it in here. Yeah, that's good. Okay, so potential difference from BC minus BD. Well, let's rewrite this. Like, what does this mean? This is the potential difference from D to C, right? D to, oops, D to C. And this potential difference is going to be 3, 2, 1. And this potential difference will be from traveling from C to D. So let's just write out the mathematical proof for that first, just to see, prove why it works. Again, we're gonna have VD to C be the electric field still constant, right? So it's negative E dot product with the L vector, where we know E already. It's negative of what's E? We got E to be this thing, right? So Q over A epsilon naught, and it's in the positive x-hat direction. Dot product, I'll write this with a big red dot, just to emphasize that, dot product with our L vector. Well, what's my L vector here? So L will be me traveling from D to C. So sorry, I meant to say, yeah, D to C. So that is going to be a distance of 2h plus h, so 3h. And I'm traveling in the negative y hat direction. So L, the distance from D to C is 3h, and my direction is going to be in the negative y hat direction. Well, what is the dot product of x hat dotted with negative y hat? That is going to be equal to 0 because, well, x hat goes in this direction, negative y hat goes in this direction. These are two perpendicular vectors, and the dot product of any two perpendicular vectors is also going to be equal to 0. So because this dot product is 0, that means this entire potential difference equation, it goes to 0. And that is our answer. And does this make sense? And it does, because we got 0, and we know conceptually that when you travel with electric field, you lose potential. When you travel against electric field, you gain potential. Sorry. And when you travel perpendicular to the electric field, you have 0 potential difference. So this does make sense why when I took the dot product, we got 0. And I think I also do a slightly better job writing this out down here. Yeah, when you do this see this on exam, if it says justify, just play it safe, write a sentence, just saying why. That makes sense. So yeah, the answer here is going to be 0, and just remember to provide your justification. Part 3 gets trickier. So what's going on here? We're now introducing a negative charge, negative 2e, placed a distance h below point position C. So remember that position C was already h below the x-axis, so we're placing this negative charge h below point C. So really this is 2h below, but whatever. Find the potential difference from VD minus VC. So notice here it's VD minus VC. So we're really traveling from BC to BD, final minus initial. So this is slightly different from part two, because now we're traveling from C to D. Earlier we were traveling from D to C. This was actually not intentional. I meant to make this also C to D, but it's a good exercise on just reading the question carefully, right? So from C to D, what's going on? Well, we can't use our uh, answer from the previous question at all, because now we're introducing this negative charge. So what are we going to do? Well, we can use the principle of superposition, because similarly, remember from test one, when you want to find the total electric field at a given point, you can add up all the electric field contributions from all the different sources at that point. And here, we're gonna just do, we're gonna find the potential difference from just the capacitor when you're traveling from C to D, and we're gonna find the potential difference of just the point charge, which is negative 2e, and we're going to add them together to find the total potential difference as we travel from C to D. Now, take a moment to think here, and what can we do to maybe simplify this process? Do we have to recalculate potential difference of a capacitor? Well, hopefully we know that we don't have to, because this entire term goes to 0. Since if traveling from C to D, we're still traveling perpendicular to the electric field, right? So because of that nice property, we don't have to worry about delta V capacitor. All we have to find is, all we have to find is delta V from the negative point charge as we move from C to D. How do we do that? Well, this electric field is no longer constant from the point charge. Now, if you're in astute student and you're good with formulas, you might remember that delta V for a point charge is just equal to KQ times 1 over R final minus 1 over R initial. Maybe you remember that, maybe you don't. This is still a good formula to remember for the test, but for the purposes of studying and just understanding what's going on, we're actually going to do the integral. So we're actually going to end up deriving this formula, which will be pretty cool. But on the actual exam, you will need to know how to find electric field from non-constant. Sorry, you are going to have to find potential difference from non-constant electric fields. So we will practice integrating again here. Horrible handwriting, but we're going to integrate. Let's see. Delta V, we're looking for delta V from the point charge. And we know that the general formula for potential difference is the negative integral of our starting position to our final position, R initial to R final, times E. And of course, we're just looking at the negative point charge. So E is from the negative point charge, dot product with DL. Now we have a lot of moving parts here. It gets a little bit tricky. So we're going to go slow here. What is the electric field? Well, the electric field of a point charge, we know from test 1, is going to be Coulomb's law, which is KQ over R squared times R hat. Remember, this is a vector. Always include your vectors. Okay. Now, we are moving from C to D. And as we're moving up here along our path, the distance from our observation to our source is changing. It's getting greater. So this R value, R being the distance from your source to your observation, is changing. It's getting greater. So we are going to represent R as a variable, which we will eventually integrate over. And the most intuitive variable to choose here should be y, right? Because we are parallel and we're along the y-axis. So I would say that r is equal to y. So in that case, r hat would just be y hat, right? Now, this is another question I got during the class session, and it's a good question. So why is r hat going to be positive y hat? Why is it not negative y hat? Because isn't the electric field going to be pointing towards the point charge? Because this point charge is negative. So naturally, you would think the unit vector should point towards the electric field. It should be negative y hat, right? But it's actually not, because remember, this is our relative position unit vector, and relative position points from the source to the observation. And remember, our observation is along this path from C to D. So if my observation is here, the relative position vector points like this. So r hat will always be positive y hat. So this formula, we're actually going to rewrite it as k. We know q is negative 2e divided by r squared, but r is equal to y in this case. So divide by y squared times r hat, which becomes y hat. Cool. So we know the electric field now. Now let's figure out what dl is. dl is pretty quick, but we still have to be careful about the direction. dl, because our variable is y, and we're traveling along the y-axis, our variable of integration should intuitively be y. So my vector is I'm gonna be in the y hat direction. Now, is it positive or negative? Let's think about that. I'm traveling from C to D, which means I'm traveling the positive y hat direction. If I was traveling from D to C, I would say I'm traveling in negative y hat direction. But C to D is going to be positive y hat. And of course, our variable of integration will be dy. So with all of this in mind, we can finally take this and plug in and simplify and solve. So delta v negative 2e is equal to the negative integral, oops, the negative integral of kq over r squared, kq, which is negative 2e over r squared but y squared, so times y hat, dot product, and I'll just write this with a big red dot just so we don't forget, dot product with our dl vector, which is positive y hat dy. Okay, make sure that's a d. Okay. One more thing is our bounds, the limits of our integral. This is super important. And another question I got a lot at the double plus session, and maybe you would naturally think, okay, C is located at a coordinate of 0, negative h, 0. So of course, I'm going to say my lower bound is negative h. My upper bound is 2h. So maybe this is our first thought, negative h to positive 2h. But remember that this is actually going to be the distance from our observation location, because we have this point charge, and we can even refer back to this formula. Like, what's our final, what's our initial? Well, our R final and our initial is going to be the distance, not the vector, not the coordinate, but the distance from our source to our observation location. So what is this distance? What's my initial distance if I'm starting at C? Well, this distance from point charge to source is going to be h. So my lower bound will be h. Notably, it's positive h because distance is always positive. Now, what is the distance from D to my observation? Now, it's not D to C. It's not D to C. Not that. It's going to be from D to my observation location. Sorry, D to my source position. And this is going to be, well, we know this is 2h down here. We know up here is also 2h. So my upper bound of this integral will be 4h. And that's just because these are distances from our source. Same thing with this formula. Okay. From here, we will simplify and integrate. So again, what's y hat dot y hat? That's going to be just 1. So yeah. This simplifies, and we can take out the constants, right? Because our variable of integration is dy, so everything that does not look like y is a constant. So let's take them out. We can take out the negative k2e, so negative 2ke, and then just the integral of h to 4h, and then this is y to the negative 2 power dy. So this becomes negative 2 ke integral of y to the negative 2 should just be negative 1 over y, right? And our bound is from h to 4h. So this gives us, well, first we can, for simplicity, just cancel out the negatives. And we get the final answer is 2ke, and it's going to be 1 over 4h minus 1 over h. And on a test, I would recommend not simplifying further because this is our final answer, and it's just constants it's just known constants that are left now. So this is our final answer. But you could take it a step further if you want. And for practice, you can simplify a bit further. So we got here, we got um oh, I see a mistake. Ah, there's a mistake here. Okay. So yeah, it's a little late. I guess I made a mistake here. The mistake I made was I accidentally dropped this negative sign. So yeah, I was looking at this and I realized it didn't make sense because 1 over 4h minus 1 over h is actually going to be negative, right? Because 1 over 4h is less than 1 over h. So this would give us a negative, but we are traveling from C to D, which means we're traveling against the electric field of this negative charge. So if I'm traveling from C to D, it's against, so we should get a positive delta V. But this is negative, so it looked a little weird. And yeah, that's because I dropped this negative sign. So because I dropped that negative sign, sorry if there's any confusion. Maybe I can um maybe I can redo this. We're Georgia Tech students. Hopefully we can just accept the fact that I missed a negative sign, so this becomes positive, and this becomes negative. So that means this becomes negative, which means, let's simplify this, this becomes negative 2 ke times 1 over 4h minus 4 over 4h. So this is going to be negative 2 ke times negative 3 over 4, which is the same as our final answer of ke 3 over 2. ke 3ke over 2h, wow, over h. So yeah, the answer key should be good. Guess I got a little flustered or tired or something there, but yeah, 3ke over 2h is our final answer. Um, yeah, it's funny. I talked about not dropping be careful about dropping the negative sign, and I dropped it. But yeah, the more practice you get, hopefully the more consistent you will be. I guess maybe a little bit out of practice or something. But that's why we're doing practice problems right now. So yeah, final answer 3ke over 2h, and we're gonna actually use that in the next problem. But before we do that, yeah, I mean, we kind of already touched on this. Justify your answer. Why is it negative? Why is it positive? Why is it zero? And we got that it was positive, and it's positive because we are traveling against the electric field. So I actually didn't write down the answer key, but I'm saying it out loud right now. So C to D, you're traveling up, but electric field points down, so traveling against the electric field. Potential difference should be positive, which is good. Okay. Question 4. An electron is now placed at rest. At position C. Find the final kinetic energy of the electron when it reaches position D. Okay. So, you place this electron at C, and it's at rest, which means that's initially no kinetic energy, and it eventually gets to point D, right? So this is an energy question, which you should expect on the test. Um, and let's just say that everything is in our system, this electron, these capacitors, they're all in our system. So the change in energy of the system is equal to 0. And that means that the change in energy is just a change in kinetic energy plus the change in potential energy in this case. Specifically, it's going to be electric potential energy. So that's going to be equal to 0. This is just restating what we wrote earlier. And K initial, K final, we are looking for the final kinetic energy. So I can rewrite delta K as just K final minus K initial plus delta V, sorry, delta U, that's a U, that's electric potential energy. I'll make that a little bit more clear. And we know in our formula sheet on the very top left that electric potential energy is equal to the charge multiplied by the potential difference. So plus Q delta V. These two are equal to each other. Okay. And all of that is still equal to 0. And we also know that it was placed at rest, which is keyword for saying it initially had 0 kinetic energy. So K final is equal to negative Q delta V. Now, this is delta B, but what is delta B here? Well, I'm starting at point C, I'm ending up at point D, so coincidentally, that means I'm moving from point C to D, and luckily, we already found that, right? From C to D, the potential difference is 3ke over 2h. So this is equal to negative Q, and then delta V is just 3ke over 2h. I think I remember that correctly, 3ke over 2h. And we know that we are placing an electron, which means Q is equal to negative E, and it's all multiplied by 3ke over 2h. So the negatives, hopefully my negatives are correct this time, cancel out, and we get a final answer of A final being equal to 3ke squared over 2h. Final answer. So yeah, we also arrived at the same conclusion here, thankfully. Right? Oh, wait, down here. Sorry. Yeah, 3ke squared over 2h. Final answer. And for a similar question, you can look at Spring 22, Test 2, Question 1. There are a lot more questions like this, but I just included one question that inspired this question for me. Question 3. Let's do problem 3 circuits. I'm gonna drink some water though. Okay, circuits. We have an ideal battery of voltage V naught equals EMF, and it's connected to capacitor with capacitance C naught, resistors with resistances R1 being 2R, and R2 being R. And the switch is initially open in the initial state, and it's initially uncharged. Super important, and let's keep that in mind. Now, before we get started, let's talk about the process, the approach to circuit questions. And maybe I should have done this a bit sooner. The approach, that is. Yeah, so taking a step back, problem 1, yeah, I meant to talk about the approach more. Problem 1, the approach for distributed charge is always find relative position vector, and then find dq using some sort of density relationship. Using that, you plug into some formula that we know. Sometimes it's Coulomb's law if we are integrating some point charge. In this case, we're integrating a rod, and we know that's the field of a rod. So we're plugging that what we just found into that formula, and we can find dE. And from then on, you just integrate, right? You integrate dE to find the total E, and just be careful about your bounds. That's the last tricky thing that requires some thinking. And don't forget if it's a vector. Question 2, for potential difference, on this exam, you should expect finding potential difference from constant and non-constant electric fields. So that probably will mean that you're going to have to do some integration over some known electric field. Now, you also should recognize when you're able to simplify it if you know electric field is uniform inside some space. And also keep in mind that electric field is, or sorry, potential difference is path independent. So I could take this path or I could take this path to get to my location. As long as I'm getting to starting at the same place, ending at the same place, the potential difference will be the same. But obviously pick the one that's most intuitive, that's makes the most sense, that makes the math the easiest. Because I wouldn't know, I wouldn't even know how to find the electric potential from taking this path, right? Yeah, so pick what's intuitive, oftentimes just a straight line, but take a step back and think about that before you start your problem. Because sometimes there's some shortcuts you can make. Be careful about notation, potential difference, mostly straightforward. Yeah, just remember, like, get practice with integrating and applying what you know. And for energy, just remember, yeah, this formula and setting up, principle of, energy principle and conservation of energy, stuff like that. But yeah, maybe that was kind of weird, like starting problem 3 and then talking about question 1 and 2. Maybe that was a good break. But right now we can dive back into problem 3. So the switch is now closed. That's our part 1. Write down 3 loop rules and 1 node rule equation for this circuit. And then we're going to calculate the current going through R1 and R2. So this will be a little bit tricky. So we'll go slow when we have to. Personally, I like to stay consistent. I always like to go from the small loops. I like to go look at the small loops first, from left to right, and then look at the big loop last. And I also like to go clockwise when I'm doing my loop rules. It doesn't matter. You could start anywhere you want, and you could go in any direction you want. Um, but I find it helps to stay consistent every single time, so you make a bit less mistakes. Um, so 3 loop rules. Let's look at my loop 1, the left inner loop. So oops, for loop 1, I am going to have, let's start at the battery. That's usually what we do. You start with EMF, and the analogy I like to think about with battery and potential difference is that there is current flowing in your circuit because the battery is providing the positive potential difference that's required. So I kind of think of this analogy as um, I have a hill. So think about potential difference, potential energy, very related concepts, right? So the battery, this EMF, provides this initial, maybe in this analogy, gravitational potential energy, um, so that the ball is high up, and the electrons, are able to roll down the hill, or in this case, the circuit. So that's kind of how I imagine this, except, it's not a perfect analogy. This battery is producing like um, it's constantly producing this potential difference, right? So whenever the battery, as long as it's, not dead, it's going to constantly be moving the electrons, or it causes the conventional current. So that's why we say when we go in the direction of conventional current, EMF is positive here. So also with this notation, I got some questions over this. The long plate is positive, the short plate is negative, and when we do these circuit analysis questions, we are always going to be going in the direction of conventional current, which means we are leaving from the positive end. So looking at it that way, right now, of course, the switch is closed. So we start with positive EMF, and what's the first circuit component we get to? Well, we go boom, boom. There's no potential drop. There's no potential difference across the switch because the switch, when it's closed, it just acts as a wire. So the switch is closed, and when we go look at our inner loop, the first circuit element we cross is this capacitor. And for capacitors, delta V of a capacitor is equal to Q over C, where Q is the total charge on the capacitor, and C is the capacitance. In this case, it's given, and it's usually given. In this case, it's C naught. But it's our job to determine whether or not this is a positive potential difference or a negative potential difference. So actually, what I should have done here, and before you do any circuit question, you should specify your direction of conventional current, which I unfortunately forgot to do. It's a little late. Apologies. Um, so here, it's most intuitive. Of course, conventional current comes out of the positive end of the battery. So it goes up and around and it splits at this junction, at this node, because this wire has this connection, it has that connection. So the current was split. So let's just call this current over here. Let's call that I2. And let's call this current on this side I3. And I named this kind of intuitively because when you just look at um, this part, all of this entire wire is in series, right? So that means all the elements in this wire segment are in series. And what does it mean to be in series? It means that you have the same current going through this entire wire. So I2 is not just this, it's also over here. And it's also down here. Um, but it's not, I2 is not this because the current will kind of split again or change differently because we still have to keep in mind of the node rule, right? Which we will set up later for this problem. But I named this I2 because oh, sorry, I meant to say I should have named this I1 because it's going through resistor 1. Just naming convention, staying consistent, making less mistakes. But yeah, so likewise, this is going to be I2 because it goes through resistor 2. And here we see, remember that the current going into a node is equal to the current going out. So these two currents are going in. So let's say for our node rule, we can just say I1 or lowercase I1, whatever. I1 plus I2 are going in, and they combine to tell us, okay, I3, I'm just going to call this, give it a new name, combines to give us I3 going out. So yeah, that is picking our direction of conventional current. Now we can actually do our loop rules. So we started with EMF, and we will see what happens when I go across the capacitor. Well, remember that when we imagine conventional current, we are imagining it's opposite to the direction of electron current. And we are going to imagine that it's carrying positive charges with it. So this is the conventional current. It's carrying a lot of positive charges. But there's a gap here between the capacitor, which means that um, all the positive charges are going to accumulate on the top side of the capacitor, which means you're going to have an excess of positive charges here, so the other plate becomes negatively charged. So what is the electric field inside this gap? Well, it's going to be positive to negative, right? So electric field inside the capacitor, you can imagine, is going to be pointing down, positive to negative. So because of that, we are still going with the conventional current. When we cross the capacitor, we are traveling with the electric field. So remember what is true about potential difference when we're traveling with the electric field? Well, we will be losing potential difference, right? So it would be negative Q over C in this case. But that could change, as we're going to see later. So in this case, at least, when we go across the capacitor, it's going to be minus Q over C. And then we're going to cross this resistor. Similarly, this is conventional current is going down through this resistor. Now, another thing to remember is that conventional current always goes in the same direction as the electric field. So if I'm going with the direction of electric field, I'm always losing potential difference. So I'm losing potential difference when I cross the R1 resistor. And remember that for resistors, potential difference is just Ohm's law, which is V equals IR, V equals IR for a resistor. And I, in this case, the current going through R1 is I1. So it's I1 times R1, but we know R1 is just equal to 2R. Okay, and by now, there are no more circuit elements to pass through. We've already gone through the resistor and the capacitor, so we can complete our loop. And we know that the round trip potential difference for any closed loop, any loop, is equal to 0. Okay. And here, let's just let's keep solving. Let's keep setting up our equations. I'm actually going to solve loop 3 next because actually why did I call this loop 2? This is loop 2. I mean loop 1. This is loop 2. But sorry if there's any confusion there. But yeah, I'm gonna solve loop 3 first, because this one is similar to loop 1 and simple. So for loop 3, this is the outer loop, you're still starting at EMF. So we're going this way. Still starting at the battery. So you have positive EMF, and when you cross the R2 resistor, you're going with the direction of conventional current, which means you're traveling with the direction of electric field, which means you're losing, be careful, you're losing electric field. Not electric field, you're losing potential difference, sorry. So EMF minus, minus I2, the current going through R2, multiply the resistance of R2, which is just going to be R in this case. So, and this is nice and simple because that's actually the only circuit element we are going to pass as we complete this loop. So this is just equal to 0. And for our second loop, this one's tricky, but I really want us to understand this. For loop 2, we're going to just imagine we start here, we go down here, and then we round trip back. This one gets tricky. I encourage you guys to kind of try this out on your own first. But yeah, let's say we start here, and then we're making our trip this way. So the first circuit element I pass is going to be R2. And don't be intimidated by the fact that we don't have a battery EMF here. Kirchhoff's loop rule will always be true no matter what. It never states that you have to have a battery or there has to be current or anything like that. As long as you have a circuit and you have a closed loop, loop rule will always be true. So we can start with our resistor here. And we're still traveling with the direction of conventional current. So we're still going to be losing potential as we cross R2. So we have negative I2 R, the potential drop across R2. Now here though, we're gonna loop up into this R1 resistor. Now remember, this is why it's important to first specify your direction of conventional current, because we said conventional current goes this way. So if my loop is now taking me up in the opposite direction of conventional current, then this is a bit different. Since I'm traveling against the conventional current, that means I'm traveling against the electric field, which means I should be gaining potential difference as I cross the resistor and even the capacitor, as we're going to see later. So all that is to say, if I'm traveling up the resistor, that means I'm traveling against the conventional current. That means I'm going to have positive potential difference. So instead of minus I1 R2, I'm actually going to have positive I1, I1 R1, which is equal to 2R. And now let's think about, okay, for the capacitor. Well, we already said we're traveling against the conventional current, so we know it has to be positive. But also just think about the fact that we already labeled this is positive, this is negative, so electric field inside the capacitor is pointing down. So of course, if I'm going up this way, I'm traveling against this electric field. So I'm, of course, again, gaining potential difference. Similar logic. So instead of minus Q over C, I'm going to have positive Q over C. So this is all equal to 0 because I've completed my loop now. So just for the sake of time and to avoid repetition, I'm going to copy and paste this for problem part 2 when we get there. But for now, we're going to finish off part 1. Now, remember that the switch, we're finding the current going through R1 and R2 when the switch is first closed, right? We just did all this work. That's only half the problem, unfortunately. So when the switch is first closed, so this is like pretty much the moment the switch is closed and you complete this circuit. And remember that initially the capacitor is uncharged. What does it mean for the capacitor to be uncharged? Well, this implies that Q on the capacitor is equal to 0. So that implies that, okay, if this Q is equal to 0, this entire term goes to 0, right? So similarly, over here, this Q is equal to 0. So a couple of these formulas actually simplify. So we are looking for R1 and R2. So what we're going to do is we're going to take this system of equations, or whatever. In this case, we actually don't have to do anything too complicated, but you can take your equations and solve for R1 and not R1, the current going through R1, which is I1, and the current going through R2, which is I2, because that's what we named them, right? In the test problem, they might already tell you this is I1, this is I2, but for the purposes of this question, we named them ourselves, which is fun. So how do I kind of find I1? Well, let's just pick my first equation here, our first loop rule. We see that Q over C is equal to 0, so EMF, this just becomes EMF minus I1 to R is equal to 0. So I1 is just equal to EMF over 2R, right? This is just going to be some algebra, right? Okay, and I2 is going to be, we can just take, whatever equation is easiest. I want to take this one. So in this one, we see that EMF is equal to I2 times R. So I2 is equal to EMF over R. And that will be our final answer for this part. And then we can check. So just to play it safe, yeah, EMF over 2R and EMF over R. And here I actually specified what I1, I2, I3 is just in case. But yeah, also the fact that the potential difference across the capacitor is 0 initially means that if there's no potential difference across that, then that means that the capacitor will act as a wire since there's no potential drop across it, or potential gain for that matter. But yeah, also don't forget your loop, your node rule, which we wrote up here. And to be totally honest, the question that you guys see on your exam will almost certainly be harder than this. It's probably going to have more circuit elements. Maybe it has more than one battery, maybe it has more than one resistor, maybe it even has more than one capacitor. So to be ready for that, you guys should really take a look at some of your GPS problems, specifically GPS 6. And I know question 3 was good. There were all the questions are good. So just make sure you guys understand how to approach these questions. But I chose this question because the algebra is simple, right? 3 linear equations, and you don't even have to do any annoying manipulation to solve it. So this is a good circuit question to just practice the fundamentals. And we saw a bit of everything. We saw what happens when we travel with the conventional current, what happens when we travel against the conventional current. And we're gonna see a few more because this is only part 1. Now for part 2, using loop rule and node rule, calculate the charge on the capacitor if you wait a long time until the circuit reaches steady state. So keyword here is going to be steady state. What does it mean for a circuit to reach steady state? That means a long amount of time has passed, which means that the capacitors, it's safe to assume that the capacitors are uh, are now fully charged. So if the capacitors are fully charged, what does that mean? Well, another important property of capacitors that you guys should remember is that when capacitors are fully charged, this implies that there's no current going through the capacitor. Now what this does not mean is that it does not mean that there's no current in the circuit. It just means that there's no current going through the capacitor part of the circuit, which means that I1 has to be what? Well, it has to be equal to 0 if there's no current going into the capacitor. And since this entire part is in series, that means there's also no current going through R1 since I1 is equal to 0. So here, what we can do is just state that I1 is equal to 0. So for that reason, any terms with I1s just cancel out because they go to 0. And for this question specifically, we are calculating the charge on the capacitor. So how can I find charge? Well, I want to find an equation for charge with only the known values and constants, right? So if I were to look at this, I have to figure out what I2 is in terms of R and EMF. That's a little bit annoying. Luckily for this question, because the equations are so simple, not so simple, but um, they're not too complicated, right? We're not forced to solve a bunch of a hard linear system. So because of that, yeah, we got a little lucky here. We're gonna take loop 1 and just solve for Q. So we see that Q is equal to C times EMF. And I really should call this C naught because in the problem, um, I wrote that the capacitance is C naught. So yeah, whatever. Q is equal to C naught EMF. And this is just going to be the answer. This one's nice and easy. But the key thing to remember here is that there's no current going through a capacitor when the capacitor is fully charged. In other words, when the circuit is in steady state. So this should, when you guys take the exam and you guys set up all these loop rule equations, node rule equations, it should help you simplify your equations a good bit, as it did for us. So let's move on to part 3. Sketch the graph. So sketch a graph on a charge as a function of time. And we just want to make sure that we label the initial and final values. So what's the initial value? Well, initially, the capacitor is uncharged. So initially, we're going to be at 0, or I should say Q equals 0. Now, we will reach steady state, which means the charge on the capacitor will approach this charge that we found, this maximum charge. So, as this is basically saying as t approaches infinity or something, a long time has passed, it's going to reach some steady state where Q is now equal to what we found earlier, C naught times EMF. So everything kind of ties in together very nicely. We found Q in the previous problem in steady state, and now we're going to model this. Now, you don't have to remember the equation for charge over time in a capacitor. You just have to know the shape. Is it going to be linear? Is it going to be like this? Or is it going to be like this? Or is it something, I don't know, something weird? Of course, it's not going to be the last option. But you guys should remember that the way I remember this is that in steady state, it's as t approaches infinity. It's kind of like you're taking the limit almost. And that means you have kind of this asymptote that you're approaching some maximum charge as time goes on. So I'm approaching this asymptote. So my graph looks something like this. And that's all you need for this question. Final value, initial value, and just remember the shape of this graph. You're not going to have to remember the equations for the differential equations for charge and current. And current we're actually going to look at right now. So make a sketch of the current going through R1 as a function of time. So why R1? Well, we're asked for R1 because something special happens to, current going through R1. The current going through R1 is I1. And initially, the capacitor was uncharged, so this capacitor just behaved like a wire. And we found I1, right? Initially, I1 was equal to EMF over 2R, so it was non-zero. And let's graph that. Initially, I1 was equal to EMF over 2R. But we saw that once the circuit reached steady state, a property of capacitors that no current goes through. So I1 became zero, as we stated here. So as t approaches infinity, or a long amount of time has passed, um, I1 is equal to zero, and the shape of this graph is going to be this exponential decay function with something that looks like this. Okay, so yeah, just remember, you have these kind of concave curves, just these curves, bonus, fun. So the circuit has now reached steady state, which means the capacitor is fully charged. We've gone over that. Um, the switch is then opened. Find the current going through R1 and R2 soon after the switch is open. So here, here this switch has been opened, unfortunately, because this, I mean, it's fine because this is a practice question. I was saying unfortunately for some reason, but yeah, the switch is, I don't know why I'm drawing the arrow. The switch is open, so there's now no current flowing through this portion of the circuit because it's no longer complete. So we can actually simplify this circuit by just focusing on this portion. So because no current's flowing through here, nothing's really happening. So this circuit can be simplified into just this capacitor, R2, R1, like just the right half if we wanted to, which we can. So we have basically this capacitor, and then this resistor, which is, I believe, R, this other resistor, which should be 2R. Now, what's going on here? Well, the battery is no longer part of the circuit. So the capacitor is now what we call discharging. Discharging. So the capacitor basically is releasing its charge, and it sort of acts like a temporary battery. So it keeps current flowing through its portion of the circuit. And because this simplified circuit is now entirely in series, that means the current is the same everywhere. So let's just call it I. But the current is the same everywhere because everything is in series now. So, this is, I guess, R2, and this is R1 over here. So we're looking for the current going through R1 and R2, but we know that's the same current. So for this question, um, we will just say, okay, well, first of all, what is the charge? What's the polarity on this plate? Well, we already stated that it's positive, negative, right? So let me just draw this down here. It's positive, negative. So the current is going to come out of the positive end of the plate, similar to a battery. So the loop rule is going to be the potential of the capacitor, which is positive. And it goes through R2 first. So it's going to be I times R minus, still the same I because the current is in series, I times 2R is all equal to 0. Now we're looking for just I. So what is Q? Well, we saw Q in part 2 is equal to Q times C naught times EMF, which means that we can just plug it in, right? Q is equal to C naught times EMF. So plug that into this equation, we see that we get C naught dot EMF over C naught because this capacitor is C naught, so I should really start writing the correct notation. But minus the rest of the loop rule, which is I times R minus I times 2R equals 0. So we see that the C naughts cancel out, and we get EMF minus 3IR is equal to 0. So it looks like EMF is, we're looking for I. So I is equal to EMF over 3R. So let's just real quickly check our answers. And thankfully, we did get the correct answer this time. So I is equal to EMF over 3R. Here, of course, in the answer sheet, the explanation is we have an open circuit, so we can ignore this portion of the circuit. So the only connection is this one, this loop. And of course, loop rule still applies, and we solve for I. Okay, that is the circuit question done now. So just to reiterate the approach, circuits start off by labeling the direction of conventional current. And if you get it wrong, it's fine. Like for example, um, you know, what if you're struggling to figure out, okay, does the current combine to go this way? Or what if I found the current to go all into the same node? That's fine, as long as you stay consistent. If I stated that I3 were pointing this way, then when I actually solved for I3, I would have gotten a negative value. And whenever you get current to be negative, that just means you chose the wrong direction. So just flip it. So if I3 was pointing this way, but I got negative, that means the current is actually pointing the opposite way. That's fine. The math will always work itself out. Don't be afraid to pick direction for the current. Just pick one that's intuitive to you and stay consistent with it as you're doing your calculations. And the math will always work itself out. Um, so yeah, set up after that, after setting the direction of current, set up your loop rule equations, your node rule equations, and chances are on a test, you're gonna have to go through some algebra, solve for some unknowns, plug stuff back in to solve for the values like I1 or I2 or something else. Um, but the steps should always be the same. And you're just going to use the same principles we used to solve this question. And another thing, just remember the properties of capacitors, what happens in steady state, what happens when it's uncharged, it behaves like a wire. When it's in steady state, there's no current going through it. And remember like the shape of these charge over time and current over time graphs. Sorry if I sound a little bit tired. We have one more question to go. Um, so yeah, extra practice, go to GPS number 6, or look at past exam questions. There's plenty of practice. You'll never run out. Or you might, and that's why we made this mock exam. But question 4, moving point charges. So let me get some more water. So moving point charge, we have an observation location at A00. Positive charge Q is moving at speed v to the right. So that's shown here, which is pretty nice in the figure. Apposition 0. Oh, sorry. It's located at 0b0. It's moving to the right at velocity v. Okay. And we have another charge, which is moving to the left at 0 negative b. So right off the bat, we can hope and pray that there's some symmetry going on, right? No, symmetry. Always nice. At the same time, another positive charge Q. Yeah, we already said that. Okay, so let's get lively. Let's solve this. What is the net magnetic field at the observation location? This is, of course, a Beat-Savart law question. So B field of moving point charges is equal to the magnetic constant, which is mu naught over 4 pi, which some people might abbreviate as just K sub m, the magnetic constant, which is fine. So mu naught over 4 pi times Q V cross R hat over R squared. Notice this is R hat over R squared, but let's simplify this. I like to use the version mu naught over 4 pi times QV cross R, not R hat, R over R cubed. So these two equations are equivalent, and you can choose whichever one you want. If possible, generally, I mean, it's always possible, but generally, I like to choose this one, just so I don't have to calculate the R hat back there. And hopefully avoid some annoying square roots. But, yeah, V is a vector, R is a vector, and we're gonna have to take the cross product of that. No getting around that. So, yeah, let's see. I want to call this top one, that's top charge 1. I want to call the second one charge 2. And I just want to focus on finding the magnetic field due to charge 1 at our observation location. Now, before we get started, let's think about what our final answer should look like. Well, from charge 1, if we do our right-hand rule, we see that, no, let's say this is charge 1. We see that our relative position vector points in kind of this direction. This points out here. And our velocity points in to the right. Our velocity points to the right. So QV cross R, if we do our right-hand rule, at the observation location, the B field from this charge should point into the page. So remember, like, your right-hand rule, right? The order matters. So V cross R, you could put your index finger towards vector V and your middle finger towards vector R, and your thumb is going to be in the direction of the magnetic field, QV cross R. So right off the bat, we know that we should get a cross product with only a Z component. So that would be a good quick check to do at the very end, a good sanity check. So what is Q? Oh, Q is just Q, but what is V? So this is gonna be mu naught over 4 pi times Q V is moving to the right at velocity at speed V, which means the vector velocity will be to the right V 0, 0. Speed V to the right, so it only has an x component, that makes sense. Cross product with the r vector, which is going to be a 0, 0. No, I forgot to find r. Sorry, ignore what I just said for the past 15 seconds. R is the relative position vector, which is equal to our observation minus our source observation, being a 0, 0 minus our source, which is from our first point charge, which is 0, b 0. This really should have been the first thing we looked for. So we get r is equal to a negative b 0. So this is our second vector in the cross product. A negative b 0 all over r cubed. What is r cubed? Well, we're gonna find the magnitude of r and then cube it. So this is gonna be the square root of a squared plus b squared. So if we cube that, that's the same as saying a squared plus b squared to the 3/2 power. Now, if you're taking linear algebra, maybe this is light work for you. If you haven't, that's fine. Just look at the formula sheet and in the math help section, they do give you the cross product formula for two vectors. And the end result should be that you get mu naught over 4 pi q, and the cross product is going to be, of course, we already know it should have a 0 in the x and y component. And if you went through with the full cross product, you're going to get sorry, uh, negative VB over a squared plus b squared to 3/2 power. Let me just check my work for a second, but that should be correct if you went through with everything. Okay, so yeah, this should be our cross product for, I should say B1, our magnetic field for B1. And it does point into the page, so good sanity check there. Because of symmetry, if we were to kind of perform the right-hand rule on the second point charge, we see that my velocity points to the left, my relative position vector points to the right. So if I do my right-hand rule, where I put my index finger with the V and my middle finger as the R, then my final position, my final direction will be my thumb pointing in the negative Z direction. So both of these moving point charges produce a magnetic field into the page at the observation location. So they add up. They're also the same distance away and moving at the same speed. So because of symmetry, we can safely say that B net is equal to B1 plus B2, which is equal to just, and again, due to symmetry, it's equal to 2 times B1. So B here is just equal to mu naught over 4 pi times Q. And I can also write this out this way. Or first of all, it's 2 times that 2Q. And I'm going to write it out as negative VB over A squared plus B squared all raised to the 3/2 power, and it's in the Z hat direction, right? All I did, just to make it look a little bit cleaner for our next problem, is I just kind of took out this vector notation and we wrote it like this. Same thing, but just multiplied by 2. Or you could just say I'm going to multiply by 2 over here and leave it at that. That's fine too. So let's just check our answer real quickly. So we get negative 2QV B over A squared plus B squared to the 3/2. And now we can take a look at part 2 of this question. Now we're placing a negative point charge, negative Q, here at the origin, as indicated in figure B. And what cardinal direction? Cardinal direction just meaning one of these 4, like northeast, southwest, up, down, left, right. In what cardinal direction must its velocity point so that the net magnetic field at the observation location is 0? So we know that the net magnetic field right now over here was into the page. So that means to create a magnetic field, a net magnetic field equal to 0, we need this point charge to create a magnetic field that points out of the page. So in other words, B1 or no B1 plus B2 points opposite of let's call this B negative Q, maybe just magnetic field from the negative Q point charge. They have to point opposite because we need B negative Q to cancel out with the previous net magnetic field we found in part 1, this. So to do that, let's just consider the we know the location, so we just have to figure out using right hand rule what direction the velocity is. So if my relative position vector points this way, what velocity do I need so that QV cross R points positive Z? So if we were to try down, we might be tempted to say V should V should point down, because when you do right-hand rule, you use this angle. You don't try to do right-hand rule across this way. Do right-hand rule looking at the smaller angle always. So when you do right-hand rule, with your index finger pointing down and your middle finger pointing right, you see that V cross R. You do see V cross R pointing. I can say V cross R will point in the positive Z direction, which sounds good initially. But remember, the full formula is QV cross R. So the Q here is negative, which means once I add that Q here, once I add that negative Q, my direction flips. So that's no good. So actually, but this still helps us because we know that all I have to do is flip the direction of V then. So if V was in that direction, then V cross R will point, if you do right-hand rule, it should point in a negative Z direction. But Q is negative. So if I have a negative out front, this becomes positive again. So V should actually point up. Very tricky. So V, what's the velocity? Wait, what kind of direction? So V, let's call this V1. V1 points up, or north, or whatever. But yeah, V1 should point upwards as we drew here. So let me specify, this is V1, this is R. Now, of course, next question is going to ask, what speed must it have so that the net magnetic field at the observation location is 0? So already this question is very similar to what you guys saw in test 1, where you calculated some electric field at some observation location. You have to figure out where to place a point charge of some magnitude Q, or some charge Q, to cancel out the previous net electric field. Similarly here, we have to figure out what velocity we need so that the net magnetic field is equal to 0. So we already know the direction. So whenever we know the direction, or we can figure out the direction, I like to just focus on magnitude, because magnitude is easy. Magnitude, we don't have to worry about signs and directions and vectors. So first of all, before we even do that, let's set up this relationship. We know that B1 plus B2, which we found from part 1 of this question, plus B of this negative charge should all equal to 0, because we want it to equal 0 at the very end. So let's just say that, okay, we know this value, they add up, and let's just say that magnitude, B1 plus B2, that magnitude has to be equal to the magnitude of this magnetic field, BQ, B negative Q. Because in order for this to cancel out with this, they have to be equal but opposite, right? So we're going to use that to help us sub and solve this equation. So already from part 2, we know what B1 plus B2 is, or sorry, from part 1, we know what B1 plus B2 is. So that's going to be, this part is going to be mu naught over 4 pi. And I'm going to say, we wrote negative VB here, but remember we're dealing with magnitude here. So I'm literally going to drop both the unit vector and any negative signs I see, because we only care about magnitude for this question, for our approach to this question. So yeah, I'm going to make this positive. I'm going to take out any unit vectors, because taking out a unit vector is not going to affect the magnitude, since the unit vector just has length 1. So don't let that confuse us. So B1 plus B2 becomes 2QVB over A squared plus B squared to 3/2. And once again, all I did was I took my answer from part 1, I took out the unit vector, and there was a negative sign here. I just removed it because magnitude is positive. This is all equal to the magnetic field of this other point charge, which we're going to set up and solve for v. So PS of Arts law still the same, mu naught over 4 pi times qv, but this is some v we found in the previous problem, right? Or the direction at least. This is v1. This is v velocity or of the negative point charge. So this is going to be, let's just call it v1, so we are not confusing it with this v or this v. So I don't want to confuse us with these other speeds that we're talking about. So we're going to call this v for this negative point charge. It's going to be v1. So q times v1 cross product with the relative position vector over r cubed should we should be able to solve for qv here. Now here let's just focus on this part. We have mu naught over 4 pi and then qv. We know that qv or at least v1 points in the y direction. It points in the positive y direction. So we know the speed is also v1. So I'm just going to say this is v1 vectors v1. So 0 v1 0. We'll make these columns more obvious. Cross product with the relative position vector, which is going to be 0. It's going to be actually I should have found this earlier, but I didn't. So the relative position vector from the point charge to our observation is going to be observation a0 0 minus source, which is located at the origin. So in this case, it's just going to be a0 0. That's our relative position vector. So yeah, cross product with a0 0. And for this, I know we said we were solving for the magnitude here. So all I have to do is I'll just say, okay, I'm gonna take this cross product. My output's a vector, but I'll just take the magnitude of that. No big deal. And we're allowed to do that. So divide that by r cubed. So of course the magnitude of our r vector here is just equal to a, because there's only an exponent. So that exponent is our magnitude. So divided by r cubed, but r is just equal to a, so a cubed. And now we have to once again compute this cross product. But it's not too bad because we have one vector that's in the y component and one vector that's in the x component. So really, you could just say that there's a shortcut with cross products, and it's that a cross b is equal to the magnitude of a times the magnitude of b multiplied by the sine of that angle between them. So you don't have to do this for this question at all. You could say that this is v1, this is my r. So and the sine, you get the sine by using right hand rule. Sorry, you get the direction by doing the right hand rule, but this gives you the magnitude of the cross product. And from here we see that if you did right hand rule, you should get something in the negative z component, but we're just taking the cross product. You can go through everything, and you should find that the magnitude of this should be at least mu naught over 4 pi times q a v1 over a cubed. So if you actually did the cross product, I think you're gonna get a negative z component, right? So because if you did right hand rule of this, this gives you an output that's in the negative z. But we're just taking magnitude, so sine of theta is the sine of 90 degrees, is just equal to 1. So for this special case, I can say that A times B, or A cross B is just equal to A times V1. And if we cared about direction, we would use right-hand rule. But we don't because magnitudes are nice. Now, also notice that we had a negative charge, right? This charge is negative, but we don't care because there's a magnitude. So I could put negative here if I want to be precise, but we're taking magnitude, so I'm just ignoring negative signs. And if I have a vector, I'm going to turn it into a magnitude after doing the cross product, of course. So that's what we did here. Now we have an expression for v1. And remember, this is still all equal to this. So we have, I'm just going to bring this back down, mu naught over 4 pi 2q v b over a squared plus b squared, all to the 3/2 power. Sorry, my handwriting is a little cramped. Here, a lot of things will cancel out. First of all, don't cancel out this v and this v1. They are two different velocities. This v came from the problem statement stating that the point charges were moving at speed v. This v1 came from what we are solving for. So we're looking for v1. But let's cross out what we can. This magnetic constant goes away. Now what else could go away? This q goes away. So already this simplifies to something a bit kinder. So 2vb over a squared plus b squared to the 3/2 is equal to av1 over a cubed. I guess I could rewrite this as a over a cubed is just a squared. So we get this. So we see that our final answer should just be v1 is equal to 2vb a squared over a squared plus b squared to the 3/2 power. Now, are we done? And if you said yes, you would unfortunately get this question. You would miss the very last point on the question at least. So, or maybe you wouldn't. I guess you wouldn't because um, because Pat was nice and he said we were looking for the speed here. So the speed would just be this. Speed is a scalar quantity and it's always positive. So yeah, this is positive. That's good. If we cared about the velocity, which is a vector, we would say that it points in the positive y-hat direction, which we already found earlier. But I guess for this question, you only care about the speed, which is cool. There's a similar question on AI Plato, question 22.9.4. I'm sure Professor Greco put that there for a reason. So yeah, use your resources, study for a test. Hopefully this video helps a bit. If it's well received, maybe we'll do it again. And maybe I'll make it record it at a more regular time. But yeah, sorry if I sound a little bit tired. Hopefully this helps. Good luck on the exam. Get plenty of rest. Needless to say. And yeah, this mock exam is just our best guess as to what could be on the exam. Still review everything at your disposal, review your GPS problems, watch your weekly topical videos if you need to learn or brush up on some concepts, do practice exam questions. But yeah, real quickly, one more minute. Distributed charge will be some sort of 2D shape. That's all I know from Professor Greco. It'll be some sort of 2D shape. And you're probably going to have to integrate over, like, find some area. In this case, a rectangle. Maybe if you were to look at problem GPS 3, question 3, you'll be integrating some sort of like disk donut shape. For problem 18.4, this is the question I had on my exam last year. It was some weird, also like kind of circular shape. Also good practice for area distributed charge problems. As to question 4 was kind of this weird sponge question. um, that you guys can also solve for great practice. Now, these are not comprehensive. There's more questions you guys can find out there, but these are the ones that quickly came to mind when we put this practice test together. And we will keep adding to this as we see questions, but for now, know what's at your disposal and um, yeah, try your best and best of luck on the exam and get plenty of rest. And for me at least, have a good night.